Those who cannot remember the past are condemned to repeat it. Those are the often quoted words of philosopher George Santayana. Another way to look at this is that it is far better than learning from one's own mistakes is to learn from the mistakes of others before you fall victim to them yourself. In this lecture, we are going to look at some of the greatest scientific blunders of the past to see exactly what went wrong. These cases demonstrate clearly why initial skepticism is the best response to any new claims. You will also see in these examples and the lessons we derive from them many of the principles, the skills of critical thinking that I have reviewed up to this point in the course. In each case, the scientists involved made major cognitive blunders. They were controlled by their own biases and blind spots, or failed to question themselves. I'm going to start with perhaps the most iconic example that I could think of, and that is N-rays. This is, I think, a great example of a scientific blunder from the past. René Prosper Blondlot, 1849 to 1930, was a French physicist who, in 1903, shortly after the discovery of X-rays by Röntgen, claimed to have discovered another form of radiation he called N-rays after his university and hometown of Nancy. He believed they were emitted by most materials, except green wood and metals that had been treated with ether. N-rays, however, were invisible. They could only be detected by refracting the N-rays through an aluminum-coated prism, which would then cause a thread coated with calcium sulfide to glow slightly. Ultimately, the detection of N-rays was dependent on the experimenter seeing this very subtle glow in the thread. Reports vary, but about 30 research teams replicated Blondlot's experiments, also seeing the glowing in the thread. There were about 300 papers total published about N-rays over a few-year period, involving over 100 different researchers. However, problems were evident from the very beginning. Many prominent labs were unable to replicate the results. N-rays appeared to have seemingly impossible characteristics. The inability to see N-rays was often explained by those believers and in yet another he replaced the N-ray source with a similarly shaped inert piece of wood, unknown to the experimenter in each case. Each time the change was not detected. So what are the lessons that we could derive from Blondlot and the other N-ray researchers who believed that they had detected N-rays? In retrospect, we know that N-rays do not exist, that the researchers were engaged simply in self-deception. They relied on subjective outcomes, their ability to see something very subtle and also at the very edge of human detection. They also relied upon very highly error-prone measurements where the effect size was smaller than the noise that was being measured. And they used these tricky measurements in order to establish an entirely new phenomenon. They were insufficiently skeptical of their own results. They used special pleading to dismiss the negative results of other researchers, like not being sensitive enough to the glow in the thread. And they did not use proper blinding to eliminate the effects of their own bias. In effect, Wood blinded the experiment for them, and when he did, the effects completely went away. They vanished. Always an indication that the phenomenon you're dealing with is likely not true. Even after N-rays were scientifically dead, Blondlot spent years of research pursuing what was ultimately a hopeless cause. Let me turn to another eerily similar example, that of Jacques Benveniste. You might think that scientists learned the lesson of N-rays a long time ago, to be properly self-skeptical, but while many certainly have, there are still those scientists who have not learned these lessons and are doomed to repeat them. Jacques Benveniste in 1988, as a researcher, thought he had discovered proof that homeopathic dilutions, extreme dilutions, diluting a substance beyond the point where any active ingredient remains, in fact, could still retain the chemical properties of what was diluted in the water. And he published these results in Nature magazine. He was studying specifically the triggering of activity in basophils, a type of immune cell, in response to an allergic trigger. Benveniste found that the basophils would react even to homeopathic dilutions of the substance, meaning that there was literally nothing left. Something that all of chemistry and biology says should be impossible. The results were dependent upon observations of a variable biological system. Again, a system where there will tend to be a lot of noise. And even subtle biases in the researchers may therefore have a profound effect. They could not be replicated in many labs, although some labs did report replication. Again, a very similar history to that of N-rays. When Benveniste's claims were met with skepticism, he claimed he was the victim of closed-mindedness, that he was being persecuted for challenging the scientific dogma of the day, that he was a modern Galileo. Benveniste also invented fanciful explanations for how the diluted solutions might work, that the antibodies communicated their effects to the basophils, perhaps not through direct chemical interaction, but remotely through radio waves, and that perhaps water could act as a template and remember these radio waves and give them off later. This even led him to believe that he could record these effects and transmit them over the phone or over the internet. However, he never tested or tried to demonstrate these assumptions. They simply were hand-waving explanations for how the impossible might be possible. He could have designed fairly objective experiments to test these basic ideas, to show if these radio waves existed. But he chose instead to stick with a much more tricky, noisy, variable biological system in order to support his claim. In an episode remarkably similar to the N-ray episode, Nature magazine, in response to criticism from the research that they published, sent a team of investigators into Jacques Benveniste's lab, including a magician and noted skeptic James Randi. They imposed rigorous blinding on the experimental protocol, and, just like with N-rays, with proper blinding, the positive effects vanished. They proved as illusory as N-rays themselves. Let's move on to yet another example of a famous scientific blunder, that of Pons and Fleischmann and their cold fusion claims. In March of 1989, Stanley Pons and Martin Fleischmann called a press conference in which they announced that they had experimentally produced cold fusion. If true, the announcement could mean a Nobel Prize for these researchers. It could also mean a revolution in energy production, an end to dependence on fossil fuels, a supply of endless, cheap, clean energy. You probably don't remember all of that happening. So what went wrong with these claims? For some background on cold fusion, Existing nuclear power plants use the process of nuclear fission to make heat, which they then use to turn a turbine and generate electricity. Fission is the process of splitting apart heavy radioactive elements like uranium. Fusion is the process of combining light elements into slightly heavier elements, such as fusing hydrogen into helium. However, tremendous temperatures and pressures are required to get atoms to fuse together. This process happens in the middle of our sun, for example, but it's difficult to generate those kinds of pressures and temperatures here on Earth outside of a large hydrogen bomb, but difficult to use for fuel. We can create these explosions, but we just can't control the reactions. We cannot do it in such a controlled way that we can use it to generate heat and produce electricity. Cold fusion, as the name implies, is fusion of light elements into heavier elements at low temperatures. This, of course, would handle the problems of having to deal with extremely high temperatures. This would be ideal for energy production, but we currently simply do not know how to accomplish cold fusion. Many researchers have tried to make cold fusion happen in their labs, but no experimental design so far has been reproducible. Often the claims are based upon measuring excess energy in an experimental setup. But there are potentially many sources of unaccounted for energy. So again, they are relying upon measuring things that are difficult to measure and there are tiny effects that are smaller than the noise of the systems that they're dealing with. There are potentially many sources of energy that are not accounted for, but any tiny bit of excess energy is taken in some cases to be evidence of cold fusion. It has been suggested, for example, that Pons and Fleischmann's setup using electrolysis to induce cold fusion in heavy water was contaminated with tritium, and that this contamination could account for these spikes in energy production that they saw, that they claimed were due to cold fusion. Pons and Fleischmann, perhaps under pressure from their institution, the University of Utah, held a press conference on March 23, 1989 to announce their cold fusion findings, prior to publishing their results in peer-reviewed journals and having their peers carefully review their results. What followed has been referred to as the fusion confusion. There were many claims coming from labs trying to replicate their findings, mostly negative. None of the positive findings, the initial positive findings, also panned out. uranium and thorium provide extra heat to the Earth. Even using Kelvin's problematic equations, radioactive decay would extend the age of the Earth to 2.7 billion years old. There are also other sources of heat that are not accounted for as well. Also, radiometric dating allowed for a highly accurate method of dating the Earth, actually a collection of methods, with current results indicating that the Earth is about 4.55 plus or minus 0.02 billion years old. This is consistent with the science of geology, which identifies many processes that would take millions or billions of years to produce the effects, the geological features that we see today. It's also compatible with Charles Darwin's evolutionary theory, which also would require hundreds of millions of years to unfold as it has. Further, nuclear fusion also provided a heat source for the sun, allowing it to burn for billions of years. Prior to the discovery of nuclear fusion and nuclear processes, it was unknown how the sun could have enough energy to exist and produce its light and heat for billions of years. There are several lessons to be learned from the history of Lord Kelvin. The first is that scientific authority can never rest in one individual, no matter how famous or successful their career. This is something that is variable culturally within science, and I think also over time. Now we're more than a century later. The scientific establishment does not rest quite as much authority in any individual. And there's a good reason for this. Any individual can be wrong, no matter how brilliant or how successful they have been. Scientific authority is better to rest in the consensus of scientific opinion among many scientists. Further, Lord Kelvin was arrogant in dismissing the findings of a scientific discipline of which he was not an expert. He thought he can use physics to casually wipe away all of the carefully accumulated arguments and evidence from geology. This doesn't make him wrong, but it should have tempered his confidence in his conclusion. This lesson is more generally applicable. Whenever a scientist or a researcher has a finding or a claim which seems to contradict a very large body of established science, they shouldn't immediately assume that they are correct and that a large body, even an entire discipline of science, is wrong. That should, if anything, make them more skeptical of their own position. And further, it would have been more reasonable to conclude from Lord Kelvin's calculations that final example, I'm going to discuss the research of John Edward Mack, a Harvard psychiatrist who began in early 1990 to investigate patients who reported that they were abducted by aliens. At first, Mack thought they might be suffering from mental illness, but most of his patients did not meet the criteria for a mental illness diagnosis. They simply didn't have the signs or the symptoms that would warrant a diagnosis of schizophrenia or any other specific mental illness. He then, therefore, began to take their reports much more seriously. In an interview, when asked if he took his patients' reports at quote-unquote face value, Mack responded, "Face value I wouldn't say. I take them seriously. I don't have a way to account for them." Mack later believed that these alien encounters might be a spiritual or transcendental experience in nature, perhaps related to the vision quests of the Native American cultures. Mack seems to have fallen victim to his patients' own beliefs or delusions. One mistake that he made was to commit the false dichotomy. He concluded that, well, these patients aren't mentally ill, therefore there is something credible about their reports. He ignored the fact that perfectly healthy individuals can, through flawed thinking and other factors covered throughout this course, arrive at firmly held but false beliefs. He ignored the fact that there was no corroborating evidence for the stories that they were telling. And he engaged in special pleading and the argument from ignorance in order to justify his conclusions. Essentially, Mack was saying that his patients were reporting what they believed were encounters with aliens, that they in fact were being abducted by aliens. He was convinced by the fact that they were sincere. They were not lying, in other words. But sincerity is not a substitute for reliability. People can be sincerely wrong. And it's odd that as a psychiatrist, he did not consider all the many ways in which people can delude themselves, even mentally healthy people, as we discussed in the lecture on delusions, and can firmly hold to a belief, especially one that is encouraged by the culture, despite evidence against their belief. All of these factors conspired to lead Mack to believe that his patients were indeed being abducted by aliens, or at the very least, something very interesting was going on. And if it was not something physical, then it was something spiritual. This, of course, led to a great deal of criticism of his conclusions, even an investigation at his institution, Harvard University. Although they ultimately concluded that Mack, what he was doing was academically reasonable, and that under the principle of academic freedom, he had the right to ask and pursue whatever questions he wished. We've spoke in this lecture about N-rays, homeopathy, cold fusion, Lord Kelvin's calculations for the age of the Earth, and alien abductions. There are many more scientific blunders that we can talk about as well, but I think these are good examples to illustrate the lessons that we have talked about in this course. In each case, the researchers failed to be skeptical of their own conclusions. They failed to learn the cautionary tales of scientists who came before them and committed their own blunders. They failed to adhere to principles of logic and to evaluate their evidence and their studies in a properly skeptical way. For example, by properly blinding studies in order to account for their evidence. Or they too heavily relied upon their own expertise or their own stature and were not sufficiently humble in the face of a genuine anomaly. There's one more example that may or may not be a real